Welcome to this video about the parametric representation of the cycloid. And we first start with a sketch. How does the curve of a cycloid arise? Here is the xy coordinate system and we draw a circle at the y-axis now. This circle here has radius r. And in addition, there is a crank firmly attached to it. So probably it is like here. This means we go from the center C of the circle to the endpoint P here. And the P actually depends on the time T. And we will then also use a parametric representation for this. So we will also right now already write xt. So this actually moved now from the original position. From the original position, it was moving omega times t. What else can we observe here? We can see that this green distance actually must be the same as the unrolled arc length here. Yeah, so probably I have to shift the whole thing a little to the left, but it's only a qualitative sketch here. So once again, this unrolled arc length here should be the same as this distance here. So before we look to the cycloid once again. What did we do? We assumed that at time equals 0, the crank is hanging straight down and the wheel begins to rotate with an angular frequency omega, and at time t we have covered an angle of omega times t, and this now creates the cycloid, which I draw here on the right side. Again, we start with the xy coordinate system. So this is now a hand drawing. You can also look to the corresponding Mathematica files for a more precise sketch. And this point P here actually is our profile of the curve xt. You see, this is not a function anymore, that as we have for one x value, we have two y values sometimes. So we actually need a curve representation. So the next task is how to find a formula for P depending on the time t. And first we describe the location of the center. So we go from origin to the center, the positional vector. The y coordinate is always the same, as the wheel here moves on this flat x axis, so it is always r, radius r, height radius r, but the x coordinate here is omega times r times t. Why is this the case? Because look at this green distance here. It is actually the x component corresponds to the unrolled arc length. So it is omega times r times t. Omega times t times radius gives this arc length here. Okay. Now we also need to include the rotational motion of the crank, of this red crank, to describe the point P. And we also want to describe the vector x. The vector x from the origin to this point P in order to get the formula. Before we can do that, we have to recall something. The so-called circular motion So I again start with the tiny sketch. Here is the XY coordinate system, and imagine now we have a circle with radius small a, and this has a parametric representation, which is cosine sine with the corresponding radius a, but we also have here a parameter t, and we are using omega t, so angular velocity omega t, and this representation, you know, is counterclockwise, mathematically positive, so this is counterclockwise. However, if you look to this original sketch, we need a rotation which is clockwise. And the second point, if you look here to this circular motion, where does it start? If you plug in 0, it starts at cosine 0, 1, sine 0 is 0, so it starts at a0, so we are actually starting here. Yeah, here is the starting point. And if you look to this wheel on the top left, we need to start down. So we need to shift the starting point also by minus pi half here. So a few modifications. What do we need here instead? First of all, the motion should be clockwise. So we again have a cosine and sine. This is the same. What does it mean clockwise? Instead of omega t, we have minus omega t. So the other direction. And as I said, already have explained, we are not starting at 3 o'clock like here. We are starting, so to say, at 6 o'clock. So we need to subtract minus pi half. So minus 90 degrees is the new starting point. Yes, and this now can be used to describe this profile xt. What is it? First you go to the center of the circle, plus, so this is the center, and now plus this circular motion with the clockwise rotation, and started at 6 o'clock minus pi half. So fine, so good. The only step what remains is to simplify this a little bit, and therefore we have to repeat some basic properties of oscillations. And first of all, recall, what about the cosine? Cosine of minus alpha, as it is an even function, is cosine of alpha. Then the sine of minus alpha is minus sine of alpha, as it is an odd function. So what does this mean here? We don't need to consider the minus inside the cosine, so I can simply write here plus plus. I can do the same with the sine, but then I have to write the minus outside in order not to change. So, and then we have two more properties. In order to simplify it further, I don't like this pi half here. And let me write the properties probably down here. So cosine of alpha plus pi half, if you remember the geometric properties, is minus sine of alpha, and the same for the sine. Analogously, it is cosine of alpha. So what does this mean here? In total, we have here omega RT and R. And instead of cosine omega t plus alpha t, I write minus sine of omega t. And similarly, R, here is a minus already was there. So I write also again minus, I forgot the A, sorry. The A should also be here. And minus A times cosine omega t. So make it more clearly visible here. Fine. This parametric representation holds for t is larger or equal 0. So I've shifted the trigonometric properties here in order to get more space for the final sketches. So we want to study the profile of the cycloid if A is larger than the radius, so the crank is longer than the radius of the circle, A is equal, and A is smaller than the radius. So for larger, you have already seen above, so it looks something like that. If it is equal the radius, you don't go below the x-axis. So these are like half circles like here. And if you are above, it is more looking like an oscillation. So if you want to play with the parameters A and R more, then just use our Mathematica notebook. Thanks for the attention and see you in the next video.